All right, last lesson of redox. This is one of my favorite things in redox. I'm definitely a super nerd though, as you know. So this is looking at our Faradays. So these are really big stoichiometric calculations. There's something satisfying when you just put so many things into a stoichiometric calculation and everything just cancels out and works so nicely. So walk through a couple examples. So when we are looking at stoichiometry in electrochemistry, you're going to find that we use a couple of additional pieces. So this isn't the same as like redox titration stoichiometry. This looks different. So these types of questions are usually going to ask you, if you run a current for a certain amount of time, how much of something could you make as that cell runs? So pieces you are going to need to be able to do this calculation. You are going to need Faraday's constant, which is 9.65 times 10 to the 4 coulombs per mole of electron. Okay, if you go to your data booklet, this is found on that miscellaneous table right here, right? So miscellaneous table is on page 3, right? This is the same spot that we look to for like KW, our quadratic formula when we were using it. But here is that Faraday's constant. So it doesn't need to be memorized. You will always have access to that. But it's 9.65 times 10 to the 4 coulombs per mole of electron. So you are going to find that we talk about current, okay? Current, which is abbreviated, or the symbol for it is a capital I, has units of amps, which are shown as a capital A. Okay, an amp is equivalent to a coulomb per second. So again, if you look in your data booklet, this is a page you guys don't look at very often, but page number 2, you will find that there's all these symbols, what it stands for, and what the units are. So here's that capital I. It stands for current. Generally, you're going to see that we're going to give you that current in amps. But what you need to do so you can do your unit analysis is recognize that an amp is the same as a coulomb per second. So we're just going to switch that unit from amps to coulombs per second. Again, you don't have to memorize it because it is in this data booklet for you. So whenever we do stoichiometry, we always need a chemical equation. What's different is when I do these types of calculations, the equation I want is just the half reaction. And the reason it's just the half reaction, have a look at Faraday's constant, right? That Faraday's constant has moles of electrons in it, which means I need to be able to cancel out moles of electrons. How I'm going to do that is I'm going to generate a ratio. Well, one part of my ratio is the moles of electron, and the other part of my ratio is whatever other thing I have, okay? So these are generally pretty large stoichiometric calculations. This is where, remember I talked about at the start of the year when we were reviewing Chem 20 stoichiometry, how you didn't really want to follow that pattern so much of like, I find moles, I do a ratio, I do what's ever left. And that's because that doesn't really work when we get into these calculations. This is where you really want to think about what's the unit I'm trying to solve for. Let me start with that, and then let me cancel everything out from there. Otherwise, I find what happens to you sometimes when you do it the other way is either you get stuck or you do all this work to realize that you've actually solved for the inverse of what you were trying to solve for. And then sometimes you recognize that, but sometimes you don't. And then what that means is everything is backwards from what it should be. So you're not even getting those individual marks for at least placing things properly because you haven't placed anything properly because you've solved for the inverse. So really important to make sure that by the time you get to the end of the calculation, you actually have solved for the units you want, okay? If you haven't solved for the units you want, then you haven't done the calculation correctly. Okay, so let's look at a couple examples, calculating different things to kind of show you how to do this so that you can. So these questions are also found in your redox booklet when you get into some of those Faradays. I can't remember exactly which questions they are, but they definitely come out of that booklet. Okay, so determine the mass of magnesium deposited at the cathode of a molten magnesium chloride electrode cell. Should say if, not is. 10 amps flow through the cell for 9.65 hours. So, first thing I need to do is I need to start by deciding what half reaction do I care about. Because it's asking me to determine the mass of magnesium deposited, I care about the magnesium half reaction. So because we're starting with a magnesium chloride molten cell, our half reaction is going to be that Mg2+. It's going to be liquid because it's molten, plus 2 electrons to give me that magnesium as a liquid. Right? So this is the same half reaction as what's in my red data booklet. The only difference is I've made these liquid instead of aqueous and solid. So we are trying to find the mass of the magnesium. Because we have mass, we need to get the molar mass, which is 24.31 grams per mole. Okay, so other information that we have for this. We know that the current is 10 amps. So remember I said when we were dealing with current, instead of writing it as amps, we were going to write it as a coulomb over a second. Okay, we also have the time given to us as 9.65 hours. Okay, like I mentioned before in these questions, we're always going to be using that Faraday's constant. So 9.65 times 10 to the 4 coulombs, and that is going to be per mole, I want to get rid of that, mole of electrons. So those are more or less the givens that I have to work with in this question. So we're going to think about what are we trying to solve for? Well, we are trying to solve for the mass of magnesium. So that means we need to get grams of magnesium. So where we have grams of magnesium is in the molar mass of magnesium. So we're going to start with that 24.31 grams, and that is going to be per mole of magnesium. Okay, so we've now placed the grams that we want. We need to get rid of moles of magnesium. We're going to get rid of moles of magnesium using a ratio. So we're going to do times. To get rid of moles of magnesium, it's going to go on the top, so 1 mole of Mg. Okay, what's going to go on the bottom is going to be our electrons, okay, because that's the other thing we have is moles of electrons inside of Faraday. So we look at this equation, there are 2 moles of electrons in it. So we're going to write 2 moles of electrons. So from this, I can cancel the unit moles of magnesium. And now the unit I need to get rid of is moles of electron. So Faraday's has moles of electrons. We're going to flip it over so that it's on the top. So we're going to do times moles of electron. I'm just going to add a couple spaces to that because it's a huge thing going on the bottom. And then on the bottom, we are going to put that 9.65 times 10 to the 4 coulombs. Okay, so now what we can cancel out is moles of electron. The next thing we need to cancel is coulombs. So we look here, there's 10 coulombs per second. The only other thing that had coulombs was this, and we've already used that. So to get rid of the coulombs, it has to go on the top, so we're going to times 10.0 coulombs over the second. So from here, we can cancel out coulombs. Okay, we're going to cancel out seconds with time. The only problem is my time here was given to me in hours, but that's okay because hopefully you know how many seconds are in an hour, right? You should know there's 3,600 seconds in every hour. Okay, if you want to do this conversion somewhere else, sometimes you guys like to do the conversion beforehand and throw the seconds in here, you can, but definitely still a good idea to make sure that you are showing that work somewhere. So now our seconds are gone. We need to get rid of hours, and so now we can times by that 9.65 hours. you have a look at those units, and now hours goes away. Okay, so much bigger stoich than what you have done in the past, right? And this is where you should start to see that that whole I find moles and then I go from there doesn't really work. Really tends to be easier to start with what has the unit you want and cancel from there. Otherwise, you guys just kind of randomly pick something and kind of hope for the best. And sometimes it works, but sometimes it doesn't. So start with what has the units you want. And then it just turns into like this canceling game and getting rid of all of those other things. Okay, so significant digits, I want to say 3. So we get 43.8 grams. Okay, so bigger stoich calculation, but really once you know how to do stoich, it's just I cancel everything. I don't have to spend too much time thinking, which is kind of nice in a unit like redox where you spend so much time thinking, memorizing, thinking, applying, and here's something that's kind of pretty straightforward. And once you practice a little bit, usually you guys find it pretty easy. So this one was solving for mass. Let's look at one where we're solving for something different. So an electroplating firm wishes to plate 12.7 grams of copper onto a pair of baby shoes from a copper nitrate solution. If a 2 amp current is used, calculate the time required and at which electrode would the shoes be attached. So we want to plate out copper from a copper nitrate solution. So that means my equation is going to be that copper 2 plus 2 electrons turning into that solid copper. So which electrode this would happen at? Well, this is reduction. Reduction always happens at the cathode. So what do we need to plate? We need to plate 12.7 grams of copper. Molar mass of copper, because I have a mass of it, is 63.55 grams per mole. What else do we have? We have been given the current, so we know that we have 2 amps. So we'll write that as 2 coulombs per second. And then the only other thing we really have would be Faradays, which would be that 9.65 times 10 to the 4 coulombs per mole of electron. Okay, so one of the weird things with time is figuring out what time you should be calculating. So generally when it comes to time, if a question specifies a time, then obviously if it says in hours, then you would be finding hours. But if it doesn't specify a time, the rule of thumb is what's a quantity of time that makes sense to the average person, right? So if you walked up to some random person and you said that amount of time, they would actually know what you were talking about, right? So if I walked up to someone and I said 3.5 hours, they'd be like, yeah, okay, I know what 3.5 hours is. But if I walked up to someone and I was like 11,342 seconds, they'd be like, I don't know how much time that is. I need to convert that over to something that actually makes sense, right? So that's kind of the general rule of thumb. So usually what we start by doing is calculating time in seconds. We see what kind of answer we get, and then we decide, does it make sense to convert it to minutes or does it make sense to convert it to hours based off of how many seconds it is, okay? So let's look at this. We are looking to calculate the time, which is t, okay? So we're going to start by finding it in seconds. So you look at all the givens we have. This one here has seconds in it, right? But right now it's on the bottom. I don't want to solve for the inverse. I want to actually solve for seconds. Sorry, my dog is dreaming on the couch next to me and is kicking her legs all over the place. Okay, so we are going to take this and we are going to flip it over so that we solve for seconds. So we're going to put the seconds over 2 coulombs. And now becomes the canceling game, right? We need to cancel out coulombs. What has coulombs? Faradays has coulombs. So we are going to times by 9.65 times 10 to the 4 coulombs per mole of electrons. So from here, we can get rid of coulombs. Okay, now we need to get rid of moles of electron. Well, I don't have any other given with moles of electron, but I can use a ratio between moles of electron and moles of copper, because then I can eventually cancel out the moles of copper. So we're going to go times 2 moles of electron over 1 mole of copper. So now we can eliminate moles of electron. Next thing we need to get rid of is moles of copper. We have that in the molar mass. We're going to take the molar mass of copper and we're going to flip it. So we're going to do times moles of copper over 63.55 grams. Now we can get rid of moles of copper. Next thing we need to do is get rid of grams of copper, and we can do that using the mass. So we can do times 12.7 grams. And from that, we get rid of grams. And so now all our units are gone except for seconds, which is a unit of time. So now we're going to calculate this to see, does it make sense to leave this in seconds or should we change it? Okay, so 19,284 seconds. So that's a very large number, right? You think about the fact that there are 3,600 seconds in an hour, probably makes the most sense to switch this over to hours. So to convert the seconds, I'm going to put the seconds on the bottom and I'm going to put the hours on the top. So we're going to do times 1 hour over 360, not 300. 3,600 seconds, sorry. And now we'll get rid of the seconds and convert it to hours. And we will get our answer. So take the answer you just had in your calculator, divide by 3,600, and we get we get to have 3 significant digits, so 5.36 hours, okay? So that turns it into a unit of time. That makes a little bit more sense, right? So that's how you calculate time. Let's do one more, calculating something different. But really you should see we're starting with what has the unit we want, and we're literally just canceling everything else out until it's all gone. Okay, if 76 grams of fluoride are required, what current would have to flow for 10 hours to produce the fluorine from molten sodium fluoride? At which electrode would this reaction occur? So we have the fluoride that we are beginning with, and this is turning into fluorine. So we are going to need 2 of these, right? Because fluorine is F2, and then we're going to put plus 2 electrons to balance that out, okay? Which electrode would this occur at? This is an oxidation. Oxidation happens at the anode. Okay, so if 76 grams of fluoride are required, so fluoride, because it's ending with "ide," implies that it is the ion, so 76 grams for this. Molar mass of just an ion is just an F, so it is going to be 19 grams per mole. Don't want that underlined. Then what else do we have? We were given the time, right? 10 hours. Apparently it is just defaulted to underlining everything. And then obviously the other thing, where did that go? Other thing we are going to have is going to be our Faraday's constant. So 9.65 times 10 to the 4 coulombs. Per mole of electron. Okay, so what are we looking for? What current? So if I am looking for current, the symbol for that is a capital I. Right, thinking units wise, although technically I'm looking to get amps because that's officially the unit, I have to remember that when I'm doing unit analysis, I'm looking to get coulombs per second because those are equal to each other, okay? So what I want to start with is kind of up to me. I either could choose to start by placing the coulombs or I could choose to start by placing the seconds. It doesn't matter. I'm going to choose to start by placing the coulombs. So 9.65 times 10 to the 4 coulombs, and that is going to go per mole of electron. Okay, I need to get rid of moles of electron because that isn't in the units that I'm trying to get. So I am going to times by 2 moles of electrons, because that's what we have in our balanced equation, over 2 moles of those fluoride ions, right? Because that's what I have a mass and molar mass for. So from here, I'm canceling moles of electron. Next thing I need to cancel is moles of F minus, so I'm going to use the molar mass to do that. So times moles of F minus over 19 grams. Okay, that's letting me cancel moles of fluoride. I need to now cancel the grams, so I can use that 76 grams. And that will now cancel my grams. Okay, so now we've placed the coulombs. Next thing we need to do is place the seconds. So again, I have been given times in hours. So I'm going to throw in that converting factor. And I'm going to put 1 hour on the top because I know that I have to put the seconds on the bottom so that the seconds is where it needs to be according to what we have said that unit is, right? So to get rid of the hours, I can then use the time that we had. So because hours is currently on top, we're going to times by 1 over 10 hours, right? And now we can get rid of the hours. Unit-wise, we are left with a coulomb over a second, which is equal to an amp. So let's type this in our calculator. And we get 11 amps because we are allowed 2 significant digits. So those are kind of the 3 things we generally ask you to calculate: time, mass, current. They're really just big unit analysis questions. Think about what's the equation I need, what's the unit I'm looking for, and then let me cancel everything until I'm left with the desired unit, okay? So that is the conclusion of redox. After this, there's only one more unit left, which is thermochemistry.